This is a double integral. What the heck is a triple integral? Triple integrals. Well, we're going to do 3 of these guys, right? And I guess one difference today, we're still going to have a function here, right, in parentheses. And we're still going to have a differential here. But I guess I want to kind of go through what we've done so far, right? So in Calc 1 and Calc 2, we used to write integral f of x dx, right? And what else did we write? This is called an indefinite integral. If I want to make it a definite integral, what else do I need notation-wise? The limits from a to b, right? Okay. And then you guys got to Calc 3, and we started doing double integrals. And how does this work? Double integral, what else do I do? Well, a couple things change. First of all, the function changes, right? So we have a function of what? Okay, 2 variables, say x and y. Another thing that changes is the differential. Instead of writing dx, what do we write? We write dA, right? Okay, so how's that going to change today? When we do triple integrals, we're going to write, yeah, the book writes dV. We write dA because A is a unit of area. We write dV because this differential is some unit of volume, right? We're recognizing a difference in dimension. In each case, what is an integral? It's the limit of a blank sum. It's the limit of a Riemann sum. And we're not going to say too much more about it. Your book does give you an outstanding picture of a triple integral Riemann sum. Let me share that with you. Triple integrals in rectangular coordinates. I mean, sometimes I look at this ebook and I'm like, this is so cool. Check this out. So, what is that? Well, that's a unit of volume, right? And so what we do, here's a picture of the XYZ plane, and we have this is sometimes called a simplex. That's a nice math word for you. But basically, it's a plane, right? It's a triangle. You could think of this as a pyramid, right? And if I restrict myself, does this make sense to you, to the first octant? What do we normally say? The first what? The first quadrant. Well, if you have a XYZ axis, I guess there's octants, right? And so the first octant would be the one where everything's positive. And that's what I'm showing you here. And if I restrict myself to the first octant, then the volume under that plane, I guess, is well, it was interesting. It's something you could compute with a geometry formula, right? But we could also do it using calculus, and some of the exercises that you've been doing, you could do them by geometry, but we're doing them with calculus to learn the process, right? And so what they get at here is, okay, when you want to approximate volume, the idea is, well, okay, you can add more z divisions, so delta zk becomes smaller. No, don't do that to me. You got to be kidding. Close the program. It looks so good, though. Oh. Well, you saw it. Okay, I'm going to move on. Okay, in the limit, the volume underneath is what we're talking about. Okay, I will have to launch that again shortly. So, for a triple integral, that was a double integral we were looking at, really, right? Except that for a triple integral, right, dV goes here. Oh, back to double integrals. I'm sorry. Back to double integrals for a second. dA goes here. What do we do instead of putting A and B? What do we do over here? So we put R. And R, you might remember, is a region on what? It's a region on the XY plane, right? And so, like, if I'm saying I'm going to evaluate volume, maybe on that last problem, my R would have been this triangle in the XY plane because it's kind of the projection of the function onto the plane, right? And so what has been really important for us when we want to do a problem that's a double integral is sometimes we'll just draw the XY plane and we'll think about, hey, what is it that makes up the region R? Is it vertically simple? Or should I be using functions of y or functions of x? Should I use polar coordinates? These are the kinds of questions you've been asking as you've been working on homework. Okay, so now what's going to happen? Well, we don't have R anymore, right? But we're going to have some solid. And this is where I want it back, because so your book uses a D, which is some three-dimensional solid object, right? So just like for double integrals, we're going to use R. Okay? This is very interesting, I think. My D here, what is D? Well, here's the triple integral, right? And so now I picture I'm in 3 space and I have, I don't know, some massive three-dimensional object instead of R, right? Or instead of, in this example, in Calc 1, what's Calc 1 look like? You integrate from A to B, right? So in Calc 1, we have a one-dimensional set we integrate over, and then the double integral was we're integrating over a region R. Now we're integrating over a three-dimensional space, which means that what goes here is a function of how many variables? 3. We're up in it. You know what's really ugly about this function? You can't graph it, right? Because if you wanted to graph that function, it would be W equals f of x, y, z, and I'm out of dimensions, guys. I can't graph that. And yet, it makes sense that quite often there's going to be functions that depend on 3 inputs. That's not out of line. You guys, the point of this section, I'm convinced, is to show you the power of Calc 3. The point of this section is to suggest that, guys, we did it. We jumped from 1 dimension up to 2. Then, today, we're jumping from 2 dimensions up to 3, or functions of 2 variables up to functions of 3 variables. Once you do that, you can do any number of dimensions. It's not any harder. I can't visualize it, just like I can't visualize this function. But I can integrate. How do I integrate? Well, what I do, you guys know the story here. We replace the dA with what? You guys know the story. dx dy, or dy dx, or we've even done r dr d theta, right? I mean, there's different ways to replace it. But what the point is that we turn it into 2 Calc 1 problems. Well, today, what do you think we're going to be doing? Take this triple integral and turn it into 3 Calc 1 problems. Okay? That's really the game. And so that's what we're going to be doing. So now, I guess one question is, are there meaningful examples that I should think about when I'm doing this? And I want to, again, go back to what we were just working on with double integrals. You guys, down here we said, if we let f of x, y always be 1. It's kind of a boring surface, right? It's just, a plane right along 1. What's really nice about that is then the double integral can be used to do what? To find the area of R. That's right. And as a matter of fact, did they do that with some of the polar coordinate problems on the homework? Because some regions are easier to find area if you're doing polar coordinates, right? And some are easier if they're rectangular coordinates. So that's an important idea. All right, guys. So what do you think we're going to do today with triple integrals? Well, what's the analogy? If we let f of x, y, z be identically equal to 1, then the triple integral, what are we going to say? Can be used to find the what? Volume of D. Right? The volume of D. So that's kind of cool. All right, what do we want to find the volume of? Well, I guess we do need some examples here. So I was looking at one feature of the ebook. They give you this quiz at the end, and I thought there were some pretty basic problems that were kind of nice. Or I could be doing quick checks if you guys like. And then the other example I saw was the example 4 I want to hit with you also. So yeah, here's a volume of a prism. That's kind of nice. We could do that. Do you guys have a preference? You guys tell me, have you looked at quick checks? Do you want me to work on the quiz, or do you like the problem you're seeing here? Resounding argument. Guys, I have to stop the argument. You can't do all of what you wanted to do, so all right. Let's go to the quiz. I just wanted to try these. So here we go. Question 1. We have a box. An iterated integral over the box. And they give me some choices. Let's see if we can answer that one, huh? Why don't you guys, I'm going to pause the tape here for a little bit and let you talk for, let's say, 30 seconds to someone near you and see if you can talk it out. And you know, I haven't taught you anything about triple integrals. I'm just having you learn based on what you know about double integrals. Does this make sense or not? I'm going to claim it does. Let's see. Hey, but you guys are telling me C? Okay. I want to use that now. I want to use that integral. Why did we say C? Because, well, first of all the integrals start from 0 to 3. And we understand that that symbol has to be paired with y. Right? Oh, so this one was easy because the only one that has dy at the end is C, right? And then, I guess, then it says we're going from -1 to 1, right? And we're talking about a box whose x-coordinates go from -1 to 1, so it must be that dx is here, right? And then, I guess the inner integral would be 0 to 2, because they tell me that y ranges, no, z ranges from 0 to 2. We already did y, so there's dz, right? And then what happens is you're integrating some function. Now, I just above this said, if we let f of x, y, z equal 1, then the triple integral actually computes the volume. Well, let's do that boring example because it's easy. 1. Okay, guys, here we go. Ready? So my black is still here with the dy. My blue is still here with the d. This is where that 4-color pen that you used to sell. I loved it. I did my math on that for years. All right. So anyways, what happens here? When you integrate 1 dz, you get z. And you're going from 0 to 2. And so then you're going to write 2 minus 0. You love, this is a tough class, guys, you know? So let's see. Now what are we doing? We're integrating black eventually, but right now I'm working on blue. I'm integrating from -1 to 1 the value 2 dx. What do you guys get? You guys are good. 2x from -1 to 1. Yeah? Which is, yeah, you know, there's that function, that problem about even and odd functions. So 2 plus 2, I get to write 2 plus 2? That's awesome. So anyways, moving on up here, I guess what I'm integrating at the end, dy, that blue thing became the number 4, Yeah? Because it's 2 plus 2 is 4. And now we're integrating from what to what? From 0 to 3. And so what do we get? 4y. Yeah. And then we write the 0 here, and we get the 3 here, and so we get 12 minus 0 is 12. Isn't that a great way to figure out the volume of that box? Or the alternative, of course, is 3 times 2 times 2. Right? So that's kind of cool. But triple integrals represent many other things. I mean, one thing you might do sometimes is you might talk about the density of an object being a function of where it is. Maybe as I get closer to the center, maybe the function is more dense. Maybe the object is more dense. I think planets might behave that way, right? So dense that it becomes solid or it becomes hot. Oh, that's another thing. A planet maybe gets hotter as it gets closer to the center. So you can imagine some applications, and actually the next section we're supposed to cover, next week, a week from today, is all about applications of double integrals and triple integrals both. Centers of mass. There's a number of nice ones, but for today they kind of just handle like kind of the theory and the mechanics behind it. Moving back. Oh, two other ideas to get across. Changing the order of integration, and then the average value of a function of 3 variables. I think I want to work on the latter next, average value, because again, if we play our game, Calc 1 to Calc 2, or Calc 1 to Calc 2 to Calc 3, it works pretty well. So let's see. Back in Calc 1, you may recall at this point, because I think we made the jump once, the average value, I was just helping a Calc 1 students with this, of f of x, okay? What you do is you integrate. So average value of f of x, let's say on the interval a, b. Okay? So again, my picture is, here's a, here's b. Maybe a is low, maybe my function is low for a while and then it gets high, and I say, well, what's the average value along AB? And I basically try and find that middle value so that this volume and the volume up there, are this area and that area are the same. And do you guys remember the formula for this? You integrate the function from a to b, but then what else do you have to do? Yeah, basically you multiply by the reciprocal of that distance, right? Because b minus a times that average value would give you the area of this rectangle. That's basically what's going on. So then we upped it a dimension, right? And so when we were doing double integrals, we talked about f of xy dA, and what you did was, okay, if we want, what's this going to be? This I'm working on now is the average value of f of xy over the region R instead of over AB, right? And so what was the deal? Well, you integrate again, but then you multiply by 1 over what? We can't do b minus a anymore. Anyways, what are we doing here? This is going to be 1 over the area of what? Of R. Now, how do you compute the area of the region R? Well, you might do that with another integral. So I've seen problems where you'll have an integral divided by an integral. Okay? Matter of fact, one way to do the area of region R is just to integrate 1, right? So you might have, the area or you might have an integral with f of xy, and then you might have another integral where you do just integrate one, and then you have the average value. And we'll see that next week also. Okay. Well, once you have that under, it's probably not going to surprise you when I show you the formula for the triple integral. Ta-da! How's that look? Yeah? They do an example. Suppose you have a block of material, 2 by 2 by 1. It doesn't say if it's feet or what it is. The picture is 2 by 2 by 1, right? So if I want to draw a picture of example 5, I have this. Let's see, x comes out 2, y varies 2, and z only comes up 1. And so what I really have, I guess, is this kind of a block. But then what they tell me is that there's heat sources on the boundaries, and the temperature in the block is given by T equals 250 xy sine of pi z. Now that's strange to me, right? Although one thing I will say, what are the values of z varying between? They said z's going between 0 and 1, right? And so what are we taking the sine of? Some number between 0 and pi. And when you take the sine of something between 0 and pi, it's positive, right? Unit circle. It's always positive in that range. And so at least what this means is I'm multiplying the temperature by something positive. Unless I'm right at the boundary, then I might be multiplying it by 0. Okay, so I guess what we're saying is the temperature up here at the top is going to be 0, and the temperature at the bottom is going to be 0. So maybe there's somehow heat inside, right? Maybe this is not totally unreasonable, but I do think this is designed by a mathematician rather than a physicist. I really do. Sometimes you can tell. Anyways, what do? It says find the average temperature of T over the block. I just thought this would be a little more interesting than just doing a random triple integral. Okay, so here I go. Can I find the average value of T over the block? So, well, again, it's 1 over the volume of D. So I'm going to write T bar, right? A lot of times, just so you guys understand, that bar is talking about a mean, right? Shoot, sorry about that. The mean average, symbol, that bar. So T bar is, well, it's going to be 1 over the, now the volume of the block here is easy, right? Because it's 2 by 2 by 1. So it's going to be 1 over 4 times the triple integral of, well, T of x, y, z dv, right? And this is the triple integral over d. And so now we just have to kind of pick, well, do you want to integrate dx first, dy first, or dz first? Sometimes you can tell based on, the function itself what you might want to do. I think my hunch here is I would do dz first. Okay, so let me give that a try. So let's see, we have 1/4, and I'm going to use the numbering I did last time. And so on the outside, we're going to have an integral, maybe I'll finish with dx. And then I'm going to have an integral dy. And on the inside, I'm going to have an integral dz. And again, what am I integrating? I'm integrating that 250 xy sine of pi z. Yep. Okay, so we're integrating from 0 to 1 dz. Oh, by the way, do you realize there's something very simple about this problem compared to the general problem? I didn't mention it yet, but I'm noticing it here as I throw in the numbers. Because isn't it true in double integrals? The outside one is always a pair of numbers, 0 to 2, right? But the inside one and a double integral, what do you usually have here? Functions, right? dy. Now it turns out that the y values here, if you look at these sides, these are the planes, right? This is y equals 0 and y equals 2, right? So it's only because we're integrating over a rectangular block that we get numbers everywhere. In general, what happens? Let's kind of show what happens in general over here. In general, you'll have a number, say a to b dx. But what will happen here, right, is you'll have some function of x. Y equals f1 of x and y equals f2 of x, right? We've seen that before with double integrals. Well, what's going to happen with triple integrals, guys? In general, when I have a dz here, this inner integral is going to be z equals some function, I'll call it g1 of what? X and y. And this is going to be z2 is some other function, or z equals g2 of x and y. And so it's just really, it's really funny how convoluted these things can get very quickly. Okay? And we'll try to be reasonable with the homework problems. We'll see how it all goes. In my mind, this stuff isn't hard. It's just more, the problems get a little more complicated. You know, it's just, can you handle all that machinery, I guess. All right, we should probably finish up. Let's see. 1/4. Antiderivative with respect to z. Well, let's see. The 250xy I'm treating as a constant right now. So let me just write down the black dx, let me write the blue dy, and then let me really work on the inside stuff. So the inside stuff, when you integrate sine of pi z, you get negative cosine, but you need to divide by pi because of the chain rule, right? So now I'm at negative 250 xy cosine, oh, I'll put over pi, let's say, cosine of pi z, and what is it I'm plugging in now? 0 and 1. You guys with me? And so again, I have a 1/4, I have an integral dx, I have an integral dy. Maybe I should start writing those zeros and twos. I'm going to need them soon. What I do is I plug in 1 and I plug in 0. So this is negative 250 over pi, and then I have an x and a y, and then I plug in, when I plug in 1, what do I get? I'm taking the cosine of pi. What's that? Negative 1. What's the cosine of 0? Positive 1, so I could subtract 1, right? So I'm basically multiplying by negative 2. Negative 2 times 250 is positive 500 over pi, and there's a 4 out front. All right. So far I have positive 500 over 4 pi. I'll do the 0 to 2 dx at the end. And right now I have, let's see, the blue one is what I'm working on now. It's 0 to 2. What am I integrating? Well, I'm just integrating xy at this point because I brought all the numbers out front. dy. guys follow? You notice when you plugged in, all the numbers came up. So I think that was kind of a nice way to do it. Sometimes there's an advantage to going one variable over the other, and that's where they talk about changing the order of integration can make a difference. So finishing up, let's see. I'm integrating dy. What do I get? I guess I get 1/2 y squared, right? So we can write...
Why isn't it 1/2 x y squared?
Well, yes. The x stays as a constant. You're right. It is 1/2 xy squared. Yeah. I didn't say it, but I meant it. So here we go. 500 over 4 pi integral 0 to 2. I have the dx on the outside. This thing I'm going to plug in a 2 and I'm going to plug in a 0. Now when I plug the 0 in and these are y values, right? Sometimes it's helpful to even write that. Y equals 0 to y equals 2. But when I plug in y equals 0, I won't see anything. When I plug in y equals 2, the 2 gets squared as 4, divided by 2 is 2. All right, so now I'll bring that 2 out front, and now I have 1,000 over 4 pi. And I'm integrating from 0 to 2. I brought all the numbers out front. I'm just integrating x dx. Man, I think I ran out of paper. Can I squeeze it? No, let's not do that. Let's draw a little arrow. I'm going to finish over there. Here we go. So I have 250 over pi when I cancel the 1,000 with the 4. Oh, and I'm integrating. What's the antiderivative of x? It's 1/2 x squared. And we're going from 0 to 2. Plug in the 2. You get 4 over 2 is 2. So I'm getting 500 over pi. So at least you've seen a triple integral sample now. Book. Do you get the same thing we do? Certainly seeing a 500 pi over pi show up. They got 2,000 over pi. What'd I miss?
No, they got the same thing. Wait a second.
No, when you square
Oh.
the x, it should have been 4. And so you have to multiply.
Let's see what happened. They did dy at the end. Let's look at our work. Off by a factor 4. You think you see it, Preston?
Yeah, and
Cool. We were here. Y squared.
No, they took the average at the end.
Oh, they did?
I think so. Well,
But-
that would explain being off by a factor of 4, wouldn't it?
Yeah, it would, but let's see what they did. We want to get this right.
Yeah.
Oh, yeah.
One of the reasons the average.
One way to do it. All right, so they just,
That's why-
I multiplied by 1/4 at the beginning, they multiplied at the end. Okay, so then they figure out 500 over pi, which is 159, they say, 0.2 units, which whatever they are, degrees, I don't know. Okay? So we do agree. Okay, so number 10 on the quiz. One way to do this problem would be to calculate the first integral, calculate the second, the third, and the fourth, and see which one is right. But that's not what I want to do, and that's not what you want to do. You know what I'd like to do? I'd like to kind of represent the integral as a picture. Matter of fact, for the sake of argument, let's pretend that f is the number 1, right? Then what I'm really doing is I'm finding the volume of this solid that the book calls D. So I feel like the thing to do for a problem like 10 is to try and represent D. And if we can do that, we can compare. So let's see if we can do that. So that first one there, okay, how would I represent D? Well, you know, one thing you might do is you kind of start to write some inequalities out, right? I mean, as I look, I'm going to work outside in, okay? So let me make this so you can see my paper and the problem. I think I can do that. Close enough. especially if I do that. There's the integral, right? So, as I'm looking at this quiz question, and it says integral from -1 to 1, and that's dx, okay? As I go ahead to represent this thing in 3 space, I can tell you right now that the number part, we're talking about the x-axis, and so everything is happening between the plane in the back and that line in the front. Everything's happening there. Okay? So those are my planes, if you want. And now as I go from 0 to 2, this is different, right? 0 to 2, dy, but here these are supposed to be functions normally. It's like f of x equals 0, or f, I could say z of y equals 0, or z of y equals 2. Now z equals 0, of course, would be this. But z equals 2 would be this line up here. Okay. So, I'm sorry, I'm in the y. I'm doing y right now. So we're between y equals 0 and y equals 2. So far, I'm in this range, right? I guess I have x is between -1 and 1. Y is between 0 and 2. And now what about z? Well, here's where things might get interesting. They say z, maybe I'll do this in green, is between y squared and 2y. But again, this is supposed to be a function of 2 variables, normally, right? It's a surface. They said z equals y squared. In other words, they don't care what x is, right? So how would I represent z equals y squared? Well, I could do this. I could draw, a parabola opening upward. But if we don't care what x is, you'd have the same parabola opening upward here. Does that look good to you guys? Can you picture kind of a solid parabola sheet that extends infinitely on that way or this way? That's the lower bound. That's surface. So, I can actually represent it, It's like, it's what the book calls a cylinder, but it's that. Right? That's this lower bound. Now, what about the upper bound? So the lower bound, this was z1, let's say, was y squared. The upper bound, z2, is equal to 2y. What does that look like? What shape is it? Yeah, I moved it down a little bit. z2 equals 2y. It's a plane, yeah. The z has to be twice as big as the y. Now, what does the plane look like? Here, let me draw it kind of in this brownish color. So let's see. I'll go right back there again. 0, 0. When y is 1, z is 2. When y is 2, z is 4. Oh, that's cool. Because 2 comma 4 is also on the parabola. So I'm picturing a line in the plane, but then I'm also picturing, this is where I'm in trouble. It's hard to do this. I'm trying to represent, again, a plane here coming out at me. And now I'm having trouble. But see, if I just zoom into the axes and just look at the YZ axis, it's much simpler. It's a line, right? Z equals 2y, and it's a parabola, z equals y squared. And so just like I did that in 2 dimensions, now if you expand it out, you're seeing what it looks like in 3 dimensions. Does this make sense to you guys? Okay, so what are we supposed to do? We're supposed to decide, hey, which of these is equivalent? What are they doing? It looks to me like they want to switch some orders of integration. Now in part A and B, they're switching and going dy dz instead of dz dy. They're leaving dx where it was. And then in part C, what did they switch? Oh, they didn't switch anything, right? Well, part C is weird because they have the inner one being numbers, and I don't see that. The inner one is supposed to be a function. So I'm going to stick with A and B as I start to do my analysis. And I guess the question is, which one of these is right? B? Because?
Because your lower bound was the line and your upper bound was the parabola. So if you set z equal to, if z is equal to y squared, if you solve that for y, you get y as the square root of z. So that's your upper bound.
Exactly. This is no harder than one of the problems you had with double integrals because this is just, we're ignoring x. So really you could solve the problem here. And we understand, again, that if I'm going to switch the order of integration, and if I'm going to do dy before dz, right, then y has to be functions of z. And I like how Kathy said, well, which one? You know, I always say top minus bottom. What do I say when it goes this direction? I say right minus left. And that's why this line will come on the bottom. What is that line? We want to write it as a function of y. So it's y equals z over 2. What is this curve? We want to write it. Well, of course, if you solve that, you get y equals plus or minus the square root of z. But this is in quadrant 1, so it really is y is the square root of z. Now, Kathy, I don't think that's as complicated as the kind of problem you're talking about, but I think it is the same idea, so I think it was worth seeing. So maybe we'll take a look at some more complicated ones here.
Can I ask a question about that?
Yep.
Because I want to make sure my brain's not thinking.
I want you to go to